Well, hello, boys and girls. Markiplier, no, Paul Yost here. Anyway, welcome to class 20. Today's going to be a relatively short lecture. I'm just going to describe Lab 8, walk you through the requirements for that lab, and then go over the lab sheet as part of that, and then I'm going to give you time to work on that today. And the lab, you should be able to get it done today if you use the lab time to work on it. So let's go ahead and get started. All right, so quick review of deadlock, since that's what this lab is about. And for a deadlock condition to exist, as a reminder, we needed 4 conditions. We need to have processes claiming exclusive control of some resource, like locking it or acquiring it and holding on to that when no one else can use it. And that resource could be locked, like a lock acquired on a file or a lock acquired on a piece of hardware or some I/O device. Or it could be something in the physical world, like if you had a tool, only one person at a time can use the tool, or a bathroom stall, only one person at a time can be in that. And then we have processes have to hold resources while waiting for other resources to become available. Resources can't be taken from a process, meaning that once a process has it, it has to release it. It can't just be forcibly taken from it. And then we have to have a circular chain of waiting that arises and exists. And if we have all 4 of those conditions at the same time, we have deadlock. And so the idea is that each process is holding on to something that another needs, but that process is also waiting on another thing that another process has. And an example of that we did a couple lectures ago was this case here where we have these cars in this intersection. This is obviously a physical embodiment of deadlock, not a programmatical embodiment. But you have this line of white cars going to the left, the line of red cars going to the right. This red car in the front wants to turn left. This white car in the front wants to turn left, going the other direction. And then they're all stuck here. And what are the 4 things there? Exclusive control of a resource. Yeah, when a car is taking up a spot on the road, another car can't coexist in that same spot at the same time due to the laws of physics. Does it hold on to that space while waiting? Yeah, when a car stops, it doesn't magically disappear and then reappear when it starts moving again. It sits wherever it sits. A resource can't be forcibly taken. Yeah, you can't have this car just shove that one out of the way or a crane come down and lift one up and move it out of there. They are where they are. And does there exist a circular wait? Well, this might work fine most of the time when there aren't cars in this configuration. But if you get this configuration, then we have a circular wait. This white one in the front is waiting on that second red one, which is waiting on the front red one, which is waiting on the second white one. And you can see that circular wait right here where they're stuck there. And unless somebody changes their mind, that is stuck forever. It's never going to move anyway. Okay, and a quick review of the dining philosophers problem, since that's what you're going to be simulating for this lab, which is kind of a fun example. So each philosopher, so they're sitting around a circular table. There are a number of plates of spaghetti, and each philosopher sits with the plate in front of them. And there are 2 forks on either side of the plate of spaghetti. And to eat spaghetti, they need to use both forks. They need to stick both in, twirl up the spaghetti on the 2 forks, and then eat. But there are the same number of forks as there are philosophers. So when, for example, me at the top here is using these 2 forks, that means that Jason and Travis can't eat because they can't get both of them, both of theirs. And if, for example, Dwayne down here gets this fork and this fork, then that means Jim and Jason have to wait because they can't get the 2 forks because Dwayne would be using them. So each one, what it does, it thinks for a bit, picks up a fork, picks up the other fork. So they pick up one, pick up the other one. They have both forks in their hands. And then they eat for a little bit and they put both forks down and they repeat that until all of the spaghetti in front of them is done. And that is what we're going to simulate in the lab today. And so think about the process by which this could deadlock. Remember that each one is thinking. Maybe with our group, it would be more about video games or programming or math than it would be about something along the lines of philosophy. Although I guess you could say that all of those things are really a form of philosophy. Maybe some of us would think about Star Trek or Star Wars or something along those lines. But anyway, the idea here is that they think for a bit, they pick up one fork, they pick up the other fork, they eat for a little while, and they put down both forks. So the idea is that how could that deadlock? Well, here's how it could deadlock. You might think, well, let's go back. You might think, well, it can't deadlock because eventually they'll get both forks, they'll eat, and they'll put them both down. But imagine that they each get ready to dine at the same time. Each one picks up the fork on their right at the same time. And then they go to pick up the fork on their left, and it's gone, so they have to wait. So in other words, I would have the fork on my right, but I would be waiting for the one on the left. Travis would have the one on his right, but be waiting for the one on the left. Jim would have the one on his right, but be waiting for the one on the left, and so forth all the way around. And Jason will be waiting on me, who's waiting on Travis, who's waiting on Jim, who's waiting on Dwayne, who's waiting on Jason, who's waiting on me, who's waiting on Travis, and you get the idea. But notice how that fits all four conditions. We have exclusive control of some resource, the fork that we have in our hand. We hold on to it while we're waiting for another one. It can't be forcibly taken away from us. We have it until we decide to set it down. And a circular weight would exist in this particular case. So you can notice how that would fit the four conditions. All right, so exclusive control, yes. Hold while waiting, yes. Resource can't be taken, yes. And in this particular case, a circular weight. Now, if we were to implement this scenario, it might not always deadlock. We might get unlucky and have it deadlock, or we might get lucky and have it so it doesn't deadlock. And in fact, deadlock might even be a really rare condition. It depends on a lot of factors. How long does it take from when we pick up one fork to when we pick up the other one? How many people are at the table? How long do we of a delay do we have between we pick up one and pick up the other one? And so forth. How many times do we need to do that? But if we don't have some control over that or some methodology to avoid deadlock or prevent deadlock or detect and recover from deadlock, it is possible that it could occur, and we could get unlucky and have that happen, which could be catastrophic in some programmatic situations. You imagine you have some emergency response system, and if that system could deadlock, it could deadlock and then prevent it from working correctly and people could die. Or imagine your airbag system in your car has a case where the software that was written to cause it to read the sensor and be deployed can sometimes deadlock. It might be a really low probability, but it could happen, and then the airbag would not deploy and somebody could die because we didn't address that. So if we have a system where we could have these four conditions, we need to recognize that and then take actions to prevent that. So lab assignment 8, you're going to be implementing a simulation of the dining philosophers. And let's go ahead and take a look at the lab sheet, and let's talk about how you might implement a solution to that problem. And let me go and switch over so you can see that lab sheet. So give me just a second here and I'll bring that up. Well, I thought I had that handy. Hold on one second. Okay, so let me switch that over so you can see what I'm seeing. Okay, so here's the dining philosopher. Let me move that over a little bit. Okay, so here's the dining philosopher problem. And looking at this, the idea is you're going to write a simple program that simulates that dining philosopher problem. So when the program's executed, it's going to prompt for a number of philosophers. I almost said falafelers, but that's like a falafel officer. Anyway, it's going to prompt you for a number. So for example, you might enter, if we wanted to simulate what we saw on the slide, we might put 5 in there. And when that program's executed, it's going to prompt for that. You're going to type in 5, and then it's going to create a thread for each philosopher. And it's the way each of those threads is going to work. It's going to work as follows. It's going to start out with a plate full of food. So I would suggest using something like an object for each of the philosophers in a thread, or you could think of it as just a spawning of this function with a thread. And you might think each one is going to start with a plate of food that's at 100%. And while there's food on the plate, in other words, while food is greater than 0, they're going to think between 0.2 and 0.6 seconds. And you can use time.sleep with random.uniform. Random.uniform generates a random number in a floating point range. So you could say random.uniform 0.2, 0.6. It'll generate a random number in that range and pass that into time.sleep. Now, then what they're going to do is pick up the fork on the left, pause for 1/100th of a second, pick up the fork on the right, pause for 1/100th of a second, and then eat for a random amount of time between 0.2 and 0.6 seconds. And then what I want you to do is after eating, we want to reduce the amount of food left on the plate. So it's going to go from 100% downwards. And I want you to drop it by a random number of points between 5 and 10. And again, you can use random.uniform or random.randint for that. And that's going to be 100 minus that. So let's say it was 10, it would drop to 90%. And then they're going to put the right fork back. They're going to put the left fork back. And then they're going to display a message saying, or then it's going to loop and keep doing that. So think, pick up left, pick up right, eat for a random amount of time, put down right, put down left, go back to the top and think again. And they're going to keep doing that until their plate is empty, meaning less than or equal to 0. And when that does get to be less than or equal to 0, then they stop and it should say, that philosopher has completed their meal. And then we should exit the thread. So a couple notes here. About implementing that. I want to have messages for each action. So in other words, philosopher 1 is thinking. Philosopher 1 picks up left fork. Philosopher 1 picks up right fork. Philosopher, instead of thinking, philosopher 1 is eating. Philosopher puts down right fork. Philosopher 1 puts down left fork, and so forth. So a message for each of those actions. And then the other thing I want you to do is think about how you'd access the forks. So for philosopher N, the 2 forks they need are going to be N, the one with their number, and 1 over from that, which would be N plus 1. But you'll need to wrap that background to 0 to fork 0 if it gets greater than the number of philosophers. So in other words, there are a couple ways you could do that with an if statement, or you could use mod, because if you use mod, it'll give you a number between 0 and the number that you mod by -1. And I'll let you think about that. But it's essentially how you'd get it to wrap around. So if you go 1 more than the number of philosophers, we've got to get it to wrap back around to 0. And keep in mind that a fork can't be held by more than 1 philosopher at a time. And I would suggest you use a lock for that. So in other words, when you get a fork, you need to lock. So what I would do if I were you is I would create a fork class with fork objects. And then I would make a fork.acquire or fork.pickup and a fork.put down. And then inside of that fork object, just have a lock and do a lock.acquire on pickup and a lock.release on put down to do that. And in order to eat, remember that each philosopher has to pick up both forks before they can actually enter this part to eat. Now, then for the main program, you're going to prompt for and have the user enter the number of philosophers, N. You're going to create N fork objects, N philosopher threads from that function. You're going to start all N philosopher threads, wait for all of them to complete, and then display a message at the end saying it's all been completed. And note that as this is written, it can deadlock. And if you run this, it might complete without deadlocking. You might run it 10 times and it might complete without deadlocking, but that doesn't mean that this is good. And again, that's one of the problems with concurrency, is that it might be unlikely that this would deadlock. If you want to kind of make it more likely to deadlock and maybe even try to force it to deadlock, if you increase the delay times here for pausing after you pick up the forks or between the 2 forks, then that will make it more likely that these will deadlock. So in other words, if you made this instead of 0.1 seconds, make that like, or 0.01, make that like 0.1 or even 0.2, it's going to be more likely to deadlock. So if you just want to convince yourself that this deadlocks, play around with changing the delay time after you pick up the left fork and before you pick up the right fork. And that's going to make it much more likely that you'll get a deadlock condition. It won't always happen, but it'll make it much more likely that it will. Now, but go ahead and run it as it is there. And what I want you to do is this program that you wrote, I want you to test it with 2 philosophers and 5 philosophers. You can try it with other numbers too, but I want you to at least test these 2 and with at least 10 runs for each. And I want you to see if it ever locks up for 2 philosophers and 5 philosophers. Now, program 2, what you're going to do is you're going to need to modify the program so that it will always complete and deadlock can never occur. And there are a number of ways of doing that, which we'll talk about here in just a second, but think about what we need to do to make that so it never deadlocks. That the only way this can deadlock is if all of them pick up the one on their left, which is what has to happen up here. They all pick up the one on their left, and then they're all waiting for the one on, they try to pick up the one on the right, and it blocks because that one's not available. So there are a number of ways to deal with that. One is you could, if you try to pick up the one on the right and it's not available, you put the one on the left back down again, and then you wait a while, some random amount of time before you pick it up again. Another way would be to modify how the order that they pick up the fork. So rather than picking up the one on the left first and then the one on the right, you might make it so that some of the philosophers pick up the one on the left and other ones pick up the one on the right. Okay, now, after you do that, I want you to test that with the same conditions, 2 philosophers and 5 philosophers each for 10 runs, or for 10 runs each for those 2. And then I want you to answer these questions. So there's a number of questions here. I want you to submit those as a text file. And question 1, did program 1 ever deadlock? And if it did, or could, I want you to describe a sequence of actions that would cause it to deadlock, referencing kind of the algorithm up here. What could happen here that would cause it to deadlock in one of those 2 scenarios that we set up? Question 2, is there a number of philosophers or a pattern of numbers for n that cannot ever deadlock? Is there some number of philosophers you could pick that would never cause a deadlock? Like, for example, with 2 philosophers, could you ever get a deadlock with 2? Or obviously, with 0 philosophers, it wouldn't do anything. What happens with 1 philosopher? What happens with an infinite number of philosophers? And obviously, infinite number, you couldn't really ever implement that because you couldn't have really an infinite size table. But just, I want you to think about that and say, is there a number or pattern of numbers that cannot ever deadlock? And then for question 3, are there numbers of philosophers or patterns of numbers that are more likely to deadlock? For example, are even numbers of philosophers or odd numbers more or less likely? Are larger numbers or smaller numbers of philosophers more or less likely? So I want you to answer that. And then for program 2, I want you to describe what you did to ensure that it won't deadlock. Like, what was your idea? What was your concept for preventing it from deadlocking? And then I want you to answer, was your solution deadlock prevention, deadlock detection and recovery, or deadlock avoidance? And I want you to, if you don't remember the distinction between those 3 categories, go back and look at the previous lecture on liveness with live lock and deadlock. And then question 6, I want you to answer, on average, will the modified program run more slowly or more quickly than the original? And I want you to justify that answer as well. So does it take longer to prevent deadlock, or keep your program from deadlocking? Does that make your program more slow or faster than it was when we allowed it to possibly deadlock? And then I have, make sure that you put that in a text file, submit that with your source code to along with the 2 programs, and submit that. So here's the output of mine running with 2 philosophers. And you'll notice that I print out the percentages. P0 is pausing with 90 left, so that's kind of where they're thinking. And then it works its way down to 0. Once they get down to 0, then they both put down their forks, and all are done. So this run did not deadlock. Now, what happens when one of these deadlocks is you'll get it where you'll see them, like P1 picks up left fork, P2 picks up left fork, and then it'll stop. The output will completely stop there. And that's with 2 philosophers. If you had 5, you'd have P1, or P0, P1, P2, P3, P4, all of them picking up their left fork together, and then all of them stopping there. But your program will never complete when it deadlocks, and that's the problem that we're trying to fix here. All right, so I wanted to keep this as a relatively short lecture. I want it to be around 15 minutes. I'm actually at 20 minutes now, but I'll go ahead and stop there. Hopefully, let's switch back to the presentation for just a second here. So we looked at that, we discussed that. So think about your process for how you think you might prevent deadlock, change your code, and do that. And again, if you want to make it more likely that your program will deadlock, increase the time between picking up the left fork and the right fork, or the time between the two forks. And that will make it much more likely to deadlock when you run it. And that way you can make sure your solution actually works. So you might play around with that. But for the final implement or submission, make sure it matches the requirements that I asked for. Okay, so that's it for today. You should probably, since I'm giving you time, you have quite a bit of time left in class today, work on that lab assignment. It really doesn't take as much code as you would think that it would. Don't procrastinate. Go ahead and get it done. Work on it today. I'm giving you time to do that. Use the in-class time that you have today to actually work on the stuff for this class, because we're going to have more stuff next week and we're starting to run out of time. So I just want to make sure you guys stay on top of things and get this last few things done. The stuff we're covering here conceptually can be very important to you writing stuff that does not have concurrent problems when you go out into the industry. And this last thing you want is to have concurrency creating non-deterministic behavior in your program. And it's those, like we said, even way back in lecture 1 and lecture 2, concurrency bugs are really difficult to reproduce and really difficult to test for. So you have to be aware of these kinds of things ahead of time and be proactive in designing your system so they don't happen. And anytime you have concurrency, you got to watch out for safety property violations, watch out for liveness property violations, and be proactive about how you write your code. So go ahead and work on that today. Get that done and submitted. And next class, we'll dig in and do a few more things. We're getting down to the end of the semester. Next week, there are a couple more topics I want to cover. And then the week after that, I'm going to post the final exam study guide and have a class period where you can ask questions and get ready for the final exam. So we really only have 2 or 3 lectures left here coming up in the next couple weeks. So stay focused on this, work on this. You're close to the end. I want everybody to be successful and learn as much as you can because this stuff is really useful, really important stuff to learn. All right, that's it. I'll stop now. It's actually at 23 minutes here. So I went over a little bit from where I wanted to be. Again, if you're confused about any of the deadlock, prevention versus avoidance versus detection or recovery, go back and watch the previous lecture on liveness, properties, live lock, deadlock. There's a couple lectures ago, but go back and watch that one if you're confused on the difference between those. All right, that's it. Everybody work on your lab, and if you get a chance, get out and enjoy the nice weather before it gets too hot. And I'll see you guys next time.